Okay, in this video, we're going to discuss section 4.3 dealing with complements and conditional probability. And in this section, we'll compute the probability of at least one occurrence of event A, and also apply the multiplication rule by computing the probability of some event, given that some other event has already occurred. Okay, so here, this is just going to be an extension of the multiplication rule to include the following two special applications. One of them, of course, is the probability of at least one. And that's where we find the probability that among several trials, we get at least one of some special event. And then number two is the conditional probability. That's where we find the probability of an event occurring when we have additional information that some other event has occurred. Okay, so now we're going to talk about complements first and how it's related to the probability of at least one. All right, now when we find the probability of some event occurring at least once, it is usually best to solve the problem backwards by working directly with the complementary event. And here, the following principles should be well known. In multiple trials, if at least one of some event occurs, then the complement or the opposite is that the event does not occur at all. So if you do not get at least one occurrence of event A, then event A does not happen at all. Okay, so at least one has the same meaning as one or more, or in some cases as an inequality greater than or equal to one. And the complement of getting at least one particular event is that you get no occurrence of that event. Okay, so here are the following steps that details this backward method of finding the probability of getting at least one of some event. Okay, so first we let A be getting at least one of some event. Then a complement would be getting none of the event being considered. So here we find the probability of a complement, which is the probability that event A does not occur. And that should be easy when we apply the multiplication rule. Then subtract the result from one. That is the equivalent to this expression. The probability of at least one occurrence of event A is equal to 1 minus the probability of no occurrence of event A. And to put that into perspective, here's the first example of that. Here I want to find the probability that when a couple has 3 children, at least one of them is a boy. And let's assume that boys and girls are equally likely. Okay. Now let's think about this. The probability of getting a boy is 1/2. And also the probability of getting a girl. Also 1/2. So here we're going to use that at least once rule. So at least one boy, we can think of this, the probability of at least one boy is going to be this, 1 minus the probability of getting no boys. Now let's think of this. The probability of no boys is the same as the probability of getting a girl. Okay, so now we're dealing with 3 children. Let's find the probability of getting 3 girls, because that's equivalent to the probability of no boys. So the probability of getting 1 girl on the first for the first child, that's 1/2. The second child, its probability of a girl is 1/2, and on the third child, that probability is also 1/2. So this is where we use the multiplication rule here: 1/2 times 1/2 times 1/2. That's equivalent to 1/8. So the probability of getting 3 girls, which is equivalent to the probability of getting no boys, is 1/8. So here we can use this 1 minus the probability of no boys. So it'll be 1 minus 1/8, because that 1/8 is also the probability of no boys. Now we need to subtract 1 whole minus 1/8. Okay, so let me use my calculator here. And then we're going to do 1 minus 1/8 will be 1 divided by 8. Then I'm going to hit the math key up here. I'm going to select the first option, which is a fraction, because I want to convert that answer into a fraction. So 1 minus 1/8 would be 7/8. So the probability of getting at least 1 boy would be 7/8. So this is how we use the backwards method for probabilities in this case. Right. Next, we'll look at conditional probability. Right. Now we now consider the second application of this section, which is based on the principle that the probability of an event is often affected by knowledge that some other event has occurred. In general, the conditional probability of an event is used when the probability is calculated with the knowledge that some other event has occurred. Okay, and this is the definition of a conditional probability. And we denote that with this, the P on the outside with the B and then the vertical bar and then A. That denotes the probability of event B given that event A has already occurred. Okay, and we can find the probability of event B given A by dividing the probability of events A and B both occurring by the probability of event A. And this is the formula that we use to find the probability of event B given that A has occurred. That's the probability of A and B divided by the probability of event A. Now, blind use of this formula is not recommended. Instead, I'm going to recommend that you use what they call the intuitive approach. And here is what the intuitive approach is. The conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. And the hint there is this: the conditional probability of B occurring given that A has already happened reduces the sample size, because you will only focus on the total number pertaining to event A. Okay. Now we're going to use that intuitive approach on these examples, like this one. In an experiment, college students were given either 4 quarters or a $1 bill, and they could either keep the money or spend it on gum. The results are summarized in the table. Complete parts A through C below. So here's that table here that you see here. Now let's look at part A. Find the probability of randomly selecting a student who spends the money given that the student was given 4 quarters. So in other words, if I write it like this, the probability that the person's or the college student spends the money given that the student was given 4 quarters. Okay, so let's start out with this. Given that the student was given 4 quarters, I'm going to highlight the row that says student given 4 quarters, because that's the only one we're going to focus on right here, that top row. The student was given 4 quarters. Let's count the total. If I add 34 and 12 together, I'm going to get 46. So we're looking at 46 students that were given 4 quarters. That's going to be your denominator. And out of the 46, how many spent the money or purchased gum in this case? And in this case, there were 34. That's how you easily come up with that answer there. The probability that a randomly selected student spent the money given that the student was given 4 quarters, that'd be 34 over 46. And as a decimal rounded to 3 decimal places, this will be approximately 0.739. Okay. So make sure that you give it, if they ask for a decimal value, you give it to how many decimal places that they ask for in the homework. All right, part B is this. Find the probability of randomly selecting a student who kept the money given that the student was given 4 quarters. Okay, spent the money given, kept the money, I'm sorry. I didn't read that. So we found the probability of a randomly selected student who kept the money given that the student was given 4 quarters. Okay, we're given that the student was given 4 quarters. We're only going to focus on that row right there. That total is 46. That would be your denominator. And out of the 46 students that were given 4 quarters, how many kept the money? In this case, 12. So that's 12 out of 46. So if I do 12 divided by 46 to 3 decimal places, this will be 0.261. Because the third digit is a 0, this 8 to the right of that will make the 0 a 1. So the probability that a randomly selected student who kept the money given that the student was given 4 quarters was 0.261. Okay, so that's how we do conditional probability here. All right, here's another example of that. The data represent the results for a test for a certain disease. Assume one individual from the group is randomly selected. Find the probability of getting someone who tests negative given that he or she had the disease. All right, so here we're looking for the probability that someone tested negative. I'll just say negative test. Given that someone had the disease. All right, so in this case here, we're given that someone had the disease. So let's focus on that. So, individual actually had the disease. That would be the yes column. I'm highlighting that. All right, so let's look at the total number of people that had the disease. If I add 138 and 9 together, I would get 147. So 147 total had the disease. That's your denominator. And out of that 147, how many had a negative test? And it will be 9. So it'd be 9 divided by 147. To 3 decimal places, that would be 0.061. So that represents the probability that a randomly selected individual tested negative, given that he or she had the disease, 0.006, 0.061. Okay. All right. Let's try this one. The table below displays results from experiments with polygraph instruments. Find the positive predicted value for the test. That is, find the probability that the subject lied, given that the test yields a positive result. Okay, so here is that table. And we're looking for the probability that the subject lied, given that the test yields a positive result. All right, let's focus on the positive result, positive test result. So I'm going to highlight that row in this table. This represents a positive test result. Let's count how many positive test results there were. So if I add 10 and 43 together, I'm going to get 53. So the denominator is going to be 53. So we have a total of 53 positive test results. Out of those 53, how many of them where, in this case, the subject actually lied? Well, the yes column means that the subject actually lied. There were 43 of those. That goes in the numerator. So it'll be 43 out of 53. So 43 divided by 53 to 3 decimal places would be 0.811. So this represents a probability that the subject lied, given that the test yielded a positive result, 0.811. Okay. Finally, we're going to talk about what they call the confusion of the inverse. To incorrectly think that the probability of event B given that A has occurred and the probability of event A given that B has occurred are equal, or to incorrectly use one value for the other, is called the confusion of the inverse. So here in general, if I take the probability of event B given that A has occurred, that is not going to be the same as the probability of event A given that B has occurred. So like in this example here, the table below shows results from experiments with polygraph instruments. And here I want to find the probability that the subject lied given a negative test result. Compare this result with the probability of selecting a subject with a negative test result given that the subject lied. Are those two equal? Okay. So here's our table. Let's find the probability that the subject lied. Given a negative test result. I'll just say negative test. All right. I'm going to highlight the row that says negative test results. That's this row right here. Now, if I add 31 and 12 together, that will give me a total of 43. So in this case, there are 43 negative test results. That's going to be in the denominator. Out of the 43, how many lied? How many subjects lied? In this case, it's 12. So here, this is 12 divided by 43. So the 3 decimal places, this will be 0.279. All right, now let's find the probability of selecting someone with a negative test result given that the subject lied. Okay, in this case here, I'm going to highlight or just box in where the subject lied. That's this column right here. Now, if I add 44 and 12 together, I'm going to get, I'll put this sum off to the side, 53. There are 53 total subjects here where the subject lied. That would be in the denominator. Out of the 53 subjects that lied, how many negative test results were there? That's 12. So in this case here, if I do 12 divided by 53, you'll see I get 0.226 rounded to okay, I made a mistake here. 44 plus 12 is 56, not 53. So I don't know where I got that from. That's 56, not 53. That will make this denominator 56. Okay, and out of the 56 that lied, 12 had a negative test result. So that's 12 divided by 56. Which will be 0.214 to 3 decimal places. Okay. So as you can basically see here, are those two probabilities equal? And the answer there will be no. Okay. So you can see those two probabilities are not the same. So the probability that the subject lied given a negative test result does not equal to the probability of a negative test given that the subject lied. Okay. So this is just an example of the confusion of the inverse. Okay. That we just got through talking about. All right, so that will conclude this video on section 4.3 dealing with complements and conditional probability. Okay. The homework should be easy for you to do. It is a short homework assignment, but do feel free to email me if you have any questions about it.